streaming and recording back on. All right, so we were here. So we just looked at the YouTube video concerning the load sensing pumps. Where is that I put my pen? Here. Okay, mathematical model for load sensing control is almost like the one we looked here. So almost a little bit like a constant pressure control. Here it is. The difference here is that Okay, so the difference is that we are monitoring the pressures from a number of the locations from the hydraulic circuit. So these are the ones, these are the locations close to actuators. So we're measuring how is the pressure right in, say, the different hydraulic cylinder. But typically these are the cylinder pressures. And we are selecting the one that is the highest. And then we make sure that the pump is capable to react to this highest pressure. There is maybe I need to make a drawing. So there are like cylinders, different kind of cylinders in your, well, this is very unclear figure. Like 4 different cylinders, and you're measuring the pressures using these pilot drives, and you're selecting the highest one. And then say here there's a pressure of 50 bar, here's a pressure of 100 bar, here's a pressure of 150 bar. The highest will be going to pump, and the pump will make sure that there's a pressure higher than the 150 bar is available right after the direction valve. If there is a set pressure difference that is, let's say, with 50 bar, it makes sure that there is a 200 bars available. So then even this big cylinder, you can lift the load. Others, you can clearly lift the load because the pressure there is much larger than is needed. So that's the kind of the idea of the load sensing control. So the extension of this previous model is simply that you have measuring the different location of your hydraulic circuit, you're selecting the highest, and that's what you're going to use in your model. Okay. Now, this was the video. This was how to get the key parameter, and this. Okay. I'm guessing that it's going to be today. The success rate will be 60%. 60. Yes, 60. Let me tell you why. Because there are 2 options that are kind of possible options. And these 2 options that are possible options are pressure for the hydraulic circuit and oil flow. And I'm saying 40% will select the pressure, 60% will select the oil flow, and that's it. But which one is correct?
Second one.
Second one.
Second one is correct.
And it will be 90%.
Yeah.
Oh, big surprise. Okay, so 94. Okay, is this trend like it's getting better and better all the time? I think what I should do is not to stop lecturing. Maybe we should just go all the way until the January or February, because the numbers is getting higher and higher. And soon when we're heading to March, we're gonna get 100%. Maybe. We'll see that. Okay, but there's going to be another in-class quiz coming soon, so be alert. That's already available. So now, example that I would like to show you is this one, and I really need to apologize because again, for some reason, when I do the conversion from my PowerPoint to this PDF, these drawings are no longer clear. So I guess that what I need to do is that I need to use a PowerPoint instead of that PDF presentation. So this is now PowerPoint, so I'm not able to write anything to the slides, but at least you can see what is a hydraulic circuit that I would like to introduce here. Okay, so here's a hydraulic circuit. Okay, so this is quite simple hydraulic circuit. I have direction valve, 3 different operation phases or different operation conditions. It's connecting 4 ports, and I have here a constant pressure source, which is this round symbol here. And then the direction valve is connected to throttle valve. So the throttle valve is the one that is here, this one here. Maybe I should even turn the camera a little bit. Maybe the online participants are able to see when I'm pointing out something in here in my my projector. Okay, so this is a throttle valve. Is it visible from the YouTube?
Yeah.
Okay, so this is a throttle valve, and it takes you to a hydraulic cylinder, and that's a piston side. Piston rod side is connected directly to direction valve. Okay, so this is my hydraulic circuit, and I want to make a model by using the first certain steps. So again, you know, it's a similar kind of idea that in a multi-body system dynamics. So we're going to follow the certain steps, and as a result of the step, we're going to get the equations that describe how much forces are coming out from the hydraulic cylinder. We have only one cylinder that we are dealing with in this example, so it's quite straightforward. All right, step number one is a drawing that shows how is it you can discretize in your hydraulic circuit, and how is it you are assuming the positive flow rate direction to be. You can do this discretization in a way that you're comparing the pressures in the locations where you are assuming pressure to be equally distributed. Flow rate, you can put any direction you want. I mean, the positive direction can be anything you want. But once you make your decision, you must be consistent. You cannot change this after that. And this is a typical mistake that people are doing when they are creating the hydraulic equations. So typically they are, you know, considering this inconsistently, the flow rate directions. So you cannot change them any longer. Like here, the flow rate comes to this volume 1. This is the one that is coming, and this is the one that is leaving. These are the way that I can define whether or not these are positive or minus sign. It's very, very important. Then I have here another volume. This is where the flow rate is coming in. You know, the piston motion, this direction, which is upright direction, will take volume off from this particular volume. And then, flow off from this particular volume. And then the piston rod side is connected to direction valve and then to tank. Okay? So this is step number one. Step number two is let's create the equations that describe the volume size. Very straightforward. The first one is simply the hose size that connects here from direction valve to this throttle. So hose diameter multiplied by its length. So simple like that. Second one, you have the hose that connects here from the throttle to cylinder plus volume associated to cylinder itself. Third one is a hose that connects the piston rod side to direction valve plus the volume in the piston rod side. Okay? So that's step number two. Step number three, compute the effective bulk models. So first one is going to be quite straightforward because the only one that affects these bulk models is a flexibility of the fluid, a flexibility of the hoses. Now, how is it you can define the flexibility of the hose? You know, okay, maybe this was a good news. Can I guess that I cannot. Here, draw. Oh yeah. Look at that. So I can make a drawing step 4.2. Oh, this is awesome. Okay, so okay, but I was in the hose. What is this? Hose 2. So what is this? I think that it is hose 1. I think that the hose is supposed to be hose 1 because it is this hose here. I believe that this is a typing mistake. This is supposed to be hose 1. PH1. This is supposed to be 1 as well. Okay, so this is the bulk modulus, effective bulk modulus for the first volume. The second volume, it is the oil, then the flexibility of the hydraulic container, which is a hydraulic cylinder, and then the hose number 2. Hose number 2 is the one that is this one here. So that's correct. And then the third one is flexibility of the fluid, then the flexibility of the hydraulic cylinder, and the flexibility of the hose number 3. Hose number 3 is the one that is connecting like this. Okay. Oh no. Not looking very good. Okay, that's fine. Okay, then we're going to form the differential equation. This is the critical thing. This is when you have to look at this drawing. And based on the drawings, you can make the, you can make decisions how is it different directions. And too bad, I have an issue here. I have an issue here because, my PowerPoint presentation is different than this one here because I made a little bit of changes to my PowerPoint presentation. Here's a class quiz. Okay, this is not gonna work out because the slides are not corresponding the in-class quizzes in Socrates. So we have to skip this because I was introducing a little bit of changes to this question because this question related to the flow here in case of this one here, this third volume is a little bit difficult. So I thought that I want to make something that is simple. I thought that I'm going to ask you this pressure number 1. And that's exactly how it reads in Socrates. I'm asking like how the pressure number 1, how you should compute that. And I had different choices such that the flow Q1 was plus minus, this one was a plus minus this Q1 A2 as well. And I was asking with the different combination which is the correct one. Obviously, this is the correct one because the flow, now I need to go back to the PowerPoint here and to show this to you. Obviously, the Q1 is calming the system. So this one is calming the system, this one is leaving. So this is where the plus and minus signs are coming from. So that's why it's extremely important to be consistent. So this is plus because it's calming the system. This is minus because it's leaving the system. Okay? Here in the second volume, this was, leaving here, but it's calming the second one. So that's what it is plus. The piston motion this direction is positive. So that's why, that when it's moving this direction, it's kind of like sucking the volume, the flow rate off from this volume. So that's what it is minus. So then the third one, the one that I was about to ask, it is actually now visible here. So it's the piston motion is going to actually, look at that. So piston motion, oh yeah, these are the different options. Not valid, not so important this time, but piston motion is actually bringing the flow rate to the system. So it's this one here, and the QB1 is the one that is leaving. So that's where the signs are coming from. Okay. My apology was not intended to be unclear. I thought that this is going to be big celebration because I'm asking something simple, and there's a big surprise. You're going to score high within class quiz. I'm not saying 100%, but I'm saying more than 60%. But that did not happen because of me. My apology. So what? Yeah, I could still ask. But now because the problem is that it's mixed. This is not synchronized with the Socrates, so you don't actually modify it in such a way that it's not going to work out today. Sorry about this. Okay, then the step number 5 is a modeling of valves and flow rates. This is very straightforward. So you just take the flow equations from the previous slides, and you're modeling with these. You can model the direction valve, the one that is shown here, in the different operation scenarios, and then you have one more flow and one more valve here, which is a throttle valve associated to this guy here. So that's how it goes. Okay. And then, oh, this is a big mess now. Now, let me see. Oh yeah, here it is correctly. Okay, let me ask this. Okay, let's ask. Okay, let's go back to this figure. Let's look at the situation. I'm asking, this first pressure, which one out of these 4 choices is the correct way to define the differential equation? Still, this is not going to be 100% success rate, because some of you were not listening to me when I was explaining this, and now suddenly it appears again. Okay. But now the choices are, you know, the positive QA1, negative QA2. Both are positive. Both are negative. And there is a negative Q1, QI1, positive QI2. How the heck you can know? That's my question. Okay, so let's look. Oh, it is on. So it is on already. So the pressure of the volume V1 can be calculated as, and then there are 4 choices, the ones that are available in the circuit. Please go and check the one that is the most appropriate one. Oh, hold on, so I'm completely confused. So I'm here. So which one is it correct? Okay, so while you, no. This, so here was a flow rate equations. Now finally, the step number 6 is to compute the force produced by hydraulic cylinder. So the pressure number 2. Pressure number 2 is the one that is applying here, minus pressure number 3, the one that is applying in a piston rod side, minus the friction model, and this is supposed to be X dot. So that's the friction model, and now I'm just assuming this to be hydraulic efficiency of hydraulic cylinder, which can be estimated to be 0.9. So it's a very simple friction model, but you know, quite good as well. So that's end of the story of the hydraulics. But now back to the in-class quiz. So let's take a look. So we have 30 answers already.
Can you show the
Yeah.
correction?
Oh yeah. So this is important. How can I show that? So where were the options?
This was in PDF, wasn't it?
Oh no. Here, this is it. These are the options. Sorry about this. Very, very confusing. Not my day today. Maybe it's yours. Maybe it's your day. Online participants, I hope they're ready as well. Okay, let me go and check it out. What was the number of answers last time? I think it was like 40, remember the number? Okay, but it seems that the number is not growing any longer. So I guess it is 41 students. So, is this it or is this not? I mean, 100% success rate. No way.
But it's over 90.
Over 90?
No.
80.
80.
It's 5.
It's
80.
under 90.
What was that? 85.
85.
And what was yours?
80 from 80 to 85.
80. Okay. Ah,
It's the same number.
it is high. It is high. Very surprised.
Yeah.
Okay, now back to this. How you know which one is correct? You know when you look at the direction of these arrows. You know this. Okay, I guess that I somehow. Oh no. You know here. You know this is the one that is coming into this system. This is the one that is leaving. So that's the way you can define that. What's the positive? What's the minus? But now I'm very much confused. Like, what is my slide right now? So I guess that I need to scroll a little bit, just check it out where I am. Here. Okay, so we're here in the flexible bodies. Now, honestly, we have 2 choices. So we can either do these flexible bodies, which is not that bad. I have a few explanations about big picture about the flexible bodies, and then it's gonna take us like say 15 minutes, and after that we're ready to move on to this real-time simulation and gamification business. Deal? Okay. So let's look at the flexible bodies. there are many ways to describe the deformable bodies in multi-body framework. Now, what is it I want to explain here? Remember the assumption we made in the very beginning of the course. We said that the bodies will not deform no matter what. And this is an assumption that is often a valid assumption, but sometimes there may be bodies that can deform. And sometimes the deformation is so significant that it actually affects the dynamic performance of your particular system. And the examples where this deformation is sometimes quite important is like cranes. So if you have a simple crane that is operated by a hydraulic cylinder, and if this bar here, if this arm is very slender structure, then it's possible, quite often it's possible that the deformation of the arm is so significant that it actually affects the performance of the structure. And you can make an estimation of this system by assuming this arm, this particular body to be rigid, but is no longer accurate representation of reality. And if it is no longer accurate representation of reality, the simulation results you will gain are no longer something that you can trust. So the way to improve the accuracy of the model is that you can introduce the ways to describe the mechanical deformation. And now there are many ways to do that. You can use a method that is called landmass approach. In this approach, you just describe the rigid body by using a number of rigid bodies that are connected together via springs that I will explain here in a second. Or you can use something that is based on the finite element method. It's kind of like a combination of finite element method and the multi-body dynamics. And that method is called floating frame reference formulation. And it is the most often used way to describe the flexibility. All the commercial softwares like Adams, Recordine, Simbach, that is coming from Germany, by the way, they are capable to describe deformable bodies, and typically they do that by using the floating frame reference formulas. And that is based on the combination of finite element model and the multi-body system dynamics. But there are special formulations, such like the absolute non-coordinate formulation, that can also describe the deformation. But they're like special formulations that are designed for really extreme cases. So what are these extreme cases? That I will explain to you next. Okay, well, this is a little bit of, before explaining what are the extreme cases, this is a little bit of background. So now, all the bodies are flexible in reality. There is no such thing like rigid bodies. Of course, no such thing, because always there is a certain amount of deformation. But when the deformation is so significant that it's actually affecting the dynamic performance, that is a little hard to define. And sometimes there are like rule of thumbs, like how to model bodies as a flexible bodies, how to model them as a rigid bodies. In reality, it's very hard to find like good rules or good formulation to define that, because it depends so heavily on the application, so heavily on the loading condition and everything. So actually you cannot really define that so well. But the flexible bodies, because we consider that the body consists of infinite number of particles. That's what we consider as a rigid body to be consisting of. Now in a flexible bodies, we have to actually eliminate the number of particles we're looking at. So we cannot no longer look at like infinite number of particles, but we're looking just at few particles, few points of the body where we are kind of estimating the deformation. And then the rest of the particles we can use in simple interpolation to estimate how they are behaving. So it's conceptually very different than rigid bodies. But the extreme situation that I was referring to you is related to amount of deformation. Amount of deformation which actually define how we deal with the linear or non-linear deformation. Okay, this is kind of important for you because the deformation, in the deformation, when we look at the deformation, there's like typically two sources of non-linearities. The first source of non-linearity is how is the relation between the displacement and strength. Okay, you know from the finite element that if you have a displacement of 1 point here, so say you have a displacement here, using the displacement you can compute the strain in any location of the structure. The first unreality, the nonlinearity is related to how is the relation between the displacement and the strain. And this is something that if you deal with the small deformation, the deformation that is not so significant, this relation can be assumed to be linear. And if you make that assumption, then you can actually see that when you're making a simple experiment where you have a cantilever beam like shown here. Now what I'm doing in this cantilever beam is that I'm loading the free end of the cantilever structure like shown here. Now if I'm assuming this strain displacement relationship to be linear, such that this is a simple relation, then when I'm loading this structure, this free end always remains in this loading line, which is all right if the deformation is small, but if deformation becomes large, then you realize that soon the deformation will be something like shown here. This free end will stay in this loading line, and you can see this is not how the beam is acting in reality. So in reality, it actually acts in such a way that if you have a cantilever structure like this, and this is an initial configuration, when it's deforming, it is deforming like this. And it's actually introducing the displacement in axial direction too. And in order to capture this, you have to introduce nonlinear strain displacement relationship. How can I say this? So a nonlinear relation between strain and displacement. This is one source of nonlinearity that is sometimes quite important when you're dealing with the flexible bodies. Okay, let me try to make this clear to you. So if you're dealing with a small deformation, then this nonlinear relation between the strain and displacement is all right. Then it behaves like shown here. In a cantilever structure, the free end of the cantilever beam remains on the loading line. But if you introduce this nonlinear behavior, then it's no longer staying in the loading line, but it's actually introducing a little bit of displacement in axial deformation. And this makes it possible to describe very large deformation. Not necessarily important in the case of cantilever beam, but in the case of belts, in case of parachutes, clothing, something that is extremely flexible like clothing like this, then you have to use this kind of nonlinear relation. And this is a typical nonlinearity in a multi-body dynamics. There's another nonlinearity available, particularly those of you that are familiar with the finite element method, you know that. And it is a relation between the strain and stresses. How is this relation? This is actually defined by material properties. And this relation could be nonlinear too. But typically this is a relation where, very beginning when you have a small deformation, there's you have seen these curves where this is a strain and this is stress. When you have a small deformation, this is a linear, it behaves in a linear way. And if you're increasing the deformation, increasing the strain, there's a nonlinear permanent deformation. This is where when there's a plastic deformation, material plastic deformation. When you take the loading off in a case like that, there will be permanent deformation in a system. And this is another source of deformation. But this is typically not so important in a multi-body dynamics, because if you have a crane that deforms a lot, it can happen. But if you have a crane but there's a material deformation, permanent deformation due to the loading, this is not very good design. You understand that if I have a crane, I lift the crane, and after the loading condition, the crane will be bended. That's not very good design. That's very bad design. And everyone will laugh to you. Okay, look at this. This guy is making this major design mistake. Now the whole thing is bended, and it looks ridiculous. So it's not a good business. So that's why typically this other source of nonlinearity is not so important in a multi-body dynamics. Okay, but I see that this is becoming a little difficult. So question to you. Okay, let me see. This geometrical nonlinearity. But yeah, so I just need to do this. Then I have here two cantilever structures. The one where there's a nonlinear strain displacement relationship, another one where there's a linear strain displacement relationship. So which one is a linear, which one is nonlinear? I guess this is clear. You know, the one here is nonlinear because it's actually moving also a little bit in axial direction. So it's making a little bit of circular shape. And because of a little bit of circular shape, the pendulum that is in the free end of the cantilever structure start actually to vibrate back and forth. This one here, I'm using the linear relationship, and then the pendulum is not introducing any kind of vibration. So this is the picture again. So that's how it looks. Okay. All right, a few more minutes and then we're done. Okay, so first method to introduce the flexibility. This was the one that based on the lamp mass approach. The idea is very simple and clean. You have original structure, like the one that is shown here. So this, where is here? Okay, so you have here, this is not the good pen, I want to use this one. So here, this is a rigid beam-like body, and you want to model this as a flexible body. So where you actually do this is that you're going to go and break this rigid body to a number of rigid bodies. So say that initial rigid body is here divided to 4 rigid bodies like shown here. And then what is that you're going to do afterwards is that you're going to introduce the spring elements such the way that there is a stiffness in all the 6 degrees of freedom with respect to these neighboring rigid bodies. So there will be spring elements, so axial spring, torsional spring, such the way that it kind of behaves as a rigid body. Strictly speaking, this is not the flexible multi-body. I'm not using the flexible multi-body theory because the equation of motion that is needed is actually one-to-one from the rigid multi-body dynamics. So the only thing that is different here is that there will be a little bit of more bodies, a little bit of more externally applied forces because the spring elements will be considered as externally applied forces. So it's quite straightforward. And a simple method too, and it can capture this nonlinear strain displacement relationship because every single element is relative displacement between the neighboring bodies. So if you keep on adding these rigid bodies, eventually you can actually describe this behavior where the strain displacement relationship is nonlinear. Here are the few examples about how it looks to have this kind of models. Oh, now I need to go back to this representation. Based on the animations, you can tell that this is not really a latest simulation or animation. So these are the ones that are made like 20 years ago, more than 20 years ago. And back then, 20 years back, this was the only method available to describe the flexibilities. Now what's very much valid at the moment is no longer this method, but the one that combines the finite element method and the multi-body dynamics. Still, this method is sometimes used. This is a meta animations that shows how it is used in a cable elements. The figures will be a little bigger than this, but soon the viewpoint will be different, and then you can see that the cable or the wire rope that is used in, here it is. So this wire rope is actually modeled by using these land mass approaches. So it's particles, rigid particles that are connected together via strings, and then it looks like pretty much how it behaves in reality. So this is still kind of valid technique in the certain special application like wire ropes. But generally speaking, the floating frame reference formulation is way more powerful, way more accurate at the moment than this method. But this example that we're looking at the moment, this is still running things in real time. So it's kind of all right application, or kind of all right method too. Okay. So soon it's going to land, and then we get to go. Okay, so here's a summary about the good things and the bad things related to this lump mass method. You know, the first negative thing is that sometimes the behavior related to high frequency may not be very accurate. It's computationally very expensive, of course, because instead of using one rigid body, you have to use a number of rigid bodies. Each one of them have to have a full set of 10 raised coordinates. And in addition to that, you have these spring elements that easily can introduce numerical difficulties. Okay? And this can be mainly used for beam-like structures. Material damping is quite simple. Computational expensive actually coming from the fact that this can easily lead to systems that are numerically stiff. The numerically stiff system is something that there is a very high frequency and very low frequencies. And this is typically something that integrators have really hard time to deal with the systems with the high and low frequencies. And there are some techniques to avoid that, and how that actually, how this is a problem in the real life. That, you know, if you want to come to this course that's starting in January, there will be a little more explanation about the stiff system, numerically stiff systems. This is easy to implement, easy to use, simple theory, because it's a linear, the rigid body dynamics, so that's why it is quite straightforward theory. Okay, what about this other method, this floating frame reference formulation, how that actually works? So it works in such that I'm going to take these kinematic equations. Let me go back here. The equations that I've introduced in this course, you know, I have here where the body reference coordinate system is located with respect to global coordinate system. Then I'm accounting the orientation of the body reference coordinate system. And then I have the particle location plus the deformation of one particular location. And this deformation here, this one here, that's the one that is coming from the finite element method. Because in a finite element method, we can compute the displacements. And this displacement we can take from the finite element method and substitute it here. So that's a kind of like a basic concept of the system. That's roughly speaking how it works. So all these U bars will be coming from the finite element method. And that's how we can actually combine two different numerical approaches, which are, you know, multi-body system dynamics and a finite element method. This figure, or this slide shows the idea. So in a finite element, we have, you know, this very good to compute the linear small deformation with respect to reference coordinate system. This is exactly what we are expecting the finite element method to do here, because we would like to model the deformation with respect to this body reference coordinate system. And this is what you can actually do by using the simple linear finite element approach as it is written here. So here, of course, this should be u dot dot. So you're solving the u dot dot, and you're actually introducing that to here. And then by using the kinematic notations as it is shown here, you can actually have very accurate representation of deformation. Now the motion of this body reference coordinate system, this one here, that is described by using multi-body system dynamics. So it's a quite beautiful method in a sense that it combines efficiently two different approaches. Okay, there's a one bot. And the one bot is related to the fact that finite element model usually, as it is, consists of very high number of degrees of freedom. So it's not unusual that finite element model have say 100,000 degrees of freedom. Sometimes it can be 1,000,000 degrees of freedom. Now things are not matching so well because, you know, here I'm using this reference coordinate system, which is a large translation and a large rotation that is described by using 6 or 7 10 raised coordinates. and then you have 1 million coordinates to describe the deformation. And this will be eventually computationally very heavy to do. So what we're doing here is that we are actually introducing a little bit of simplification. So we are actually reducing the model size by using a model reduction techniques. And in model reduction techniques, we are actually looking at the assumed deformation modes of the structure. And this is what we can actually use in order to describe the deformation. This will significantly reduce the size of the finite element model, but of course will affect a little bit about the accuracy, but not that much. And using this kind of mapping from nodal coordinates to modal coordinates, we can introduce something that is quite significant and very important. Okay, examples. Oh, now I need to go back to this. How these modal coordinates, how they look like. So here's a tibia phone. So this is how they look like. Now the frequencies are not available here, but you can see this is a kind of like natural frequencies and natural deformation modes of this one particular bone. Now using this kind of information, we can combine the finite element model and the multi-body dynamics. And once we do that, then we can run examples like this biomechanical example where the bones are assumed to be flexible bodies. And we can measure the strains and stresses in both the bones in different exercises. So everything will be based on these assumed deformations. And the assumed deformation is just use a model reduction. And I know for a fact that there is not much you can learn from this because it's I'm sure the way you hear me is like this and that, but that's all right because this is just a highlight. If there's something to remember would be this one. There is a way to combine finite element method and the multi-body dynamics. Why you should do that? Well, you should do that in order to make more accurate models or in order to measure the strains and stresses. And this method is called floating frame of reference formulation. You're good. Alternatively, use a method shown here when you take a rigid body and you kind of break the rigid bodies, the number of rigid bodies. And between these rigid bodies, you're introducing the spring elements. Okay, so I can see that there is only 2 minutes left. So I guess that not enough to open the topic of real-time simulation, but that will be next time. And again, next time is not going to be next Tuesday, but Tuesday after that. Okay, so let me ask you this. What you just heard, say last 10 minutes, that was the hardest so far. Was it not? Pretty much. That's all right, because this is like a little bit of supplementary material and not core content. Not the core content. But the next is a real-time simulation and the games, and that's going to be extremely, extremely enjoyable. So I'm asking your opinions. Are we going to sing a song about the real-time simulation, group hawk, this kind of stuff? Okay. No, not next Tuesday, but Tuesday after that. I'm going to send you a reminder regarding the organizational lectures via Moodle. So with that, I guess that we can close for today. Okay, thank you, and I'll see you on after 2 weeks. And that's when we're going to close the course. Oh, by the way, how is my voice, by the way? It seems that, oh yeah, I hope that it's been all right all the time.
Yeah.
So it's been all right all the time. Okay, very good.